Thank you, Ru. The goal in focusing is to design waveforms that upon propagation inside a medium would focus their energy at a specific time and location. Focusing has applications in many areas of science and engineering. But in geophysics, for example, it has applications in microseismic monitoring, and it's also fundamentally and conceptually related to the problem of focusing, imaging. There are various techniques available for achieving a focus, but one of the most frequently used one is the technique based on the time reversal invariance of the wave propagation operator. The method is called the time reversal, and it's the simple basic, it comprised of 3 basic steps, which I'm going to illustrate to you here with this cartoon. Imagine we have a heterogeneous medium, and the heterogeneity inside the medium is represented by the gray stuff. I have a source somewhere inside the medium. Now I've surrounded the medium with stations which are capable of both receiving and also propagating waves. Now throughout this presentation, whenever a station is colored blue, that means it's in receiving mode, and whenever it's colored red, that means in propagation mode. So if the source is activated, the waves propagate and they eventually get recorded by each station. So each station records a time trace. And then the next step, we get each trace and time reverse it in the sense that this first sample becomes the last and the last becomes the first. And finally, in the third step, the stations switch role and they become injectors. And each one inject their own time reverse signal. A new waveform is created and it propagates backwards towards the original source location. And a focus eventually is created. So this is time reversal in a nutshell. However, there are some issues. The first and most important problem is that in reality we often don't have the luxury of surrounding our medium with stations like this. And what we can achieve is more likely to be a situation like this, where we only sample the wave field at limited and scattered locations. And it has some detrimental effects on the quality of the focus that we can achieve with time reversal. But there is some more. And let me explain to you what the other issues are by showing you a numerical example. Here I'm showing you a 2D model of acoustic velocities, and I've surrounded this model with seismic stations again. I have a source inside the medium, and if I switch to the wave field, the source is injected at time 0, and then the waves start propagating. And they eventually get recorded by each station, and then each station becomes an injector, and they inject the time reversed signals back into the medium. The new waveforms propagate backwards, and this is the best focus that we can achieve at the time of focus. I'm saying the best because there's a fundamental limitations for time reversal process, and it's called the diffraction limit. It basically states that the size of the focus is comparable to the half of the dominant wavelength in our wave field. So this is a fundamental barrier. Now to show you what happens if I don't have the complete aperture, I'm going to get rid of most of these stations and only keep 5 of them to the top right. And I will repeat the experiment and show you the result of focus at the time 0 of focus. And this is the result. As you can see, the size of the focus has been extended in a certain direction. And we also have abundant side energy at areas far away from the actual focus location, which the energy now is relatively high with respect to the main lobe. Apart from these, in reality, we often have dissipative media. That means as wave propagate, they lose some high frequency energy. And whatever information is lost due to dissipation cannot be recovered by time reversal process. So I have given you three main problems with the time reversal method: the incomplete acquisition, the diffraction limit, and attenuation. And because of these problems, time reversal cannot perform optimally. The question that I want to answer is that what we can do instead of just time reversing and injecting this signal back into the medium in order to achieve a better focus beyond the time reversal method in the presence of these limitations. And this brings me to the solution that I want to provide to this problem. Basically, I will cast focusing as an optimization problem. The easiest way I can explain this is as follows. Imagine I have a medium where I know the velocity of wave propagation inside the medium. And I have a bunch of receivers, n of them on top. Now if I let one of these stations, let's say the station at Ri inject an impulsive source, then at an arbitrary location R in the medium, what I would record is the Green's function associated with the source at Ri and recorded at R. If instead of a delta function, an impulse, I inject an arbitrary time series signal, then the wave field at R would be the convolution of A, the time signal, and the Green's function. And of course, if I let each station inject their own specific and different time series, then the wave field at R would be the sum of these convolutions. Convolution in time domain becomes multiplication in frequency domain. So if I take this formula for the wave field and write it in the frequency domain, I can express each frequency component of the wave field as a weighted sum of the Green's functions. And these weights, A sub I that's of omega, are what I have control over and I want to determine to get the result that I want, which is focusing at a specific target. Let's say I want to focus at location RF, somewhere inside the medium, and F here stands for focus. So this means that ideally I would want my wave field to be nearly zero at all locations and at all times except for one location and one time, which is the location of the focus, RF, and the time of focus, which we take to be zero. And symbolically I can express it as this, which I'm saying that I want my wave field to approach to the product of two Dirac delta functions, one spatial with support at RF and one temporal with support at time zero. If I take this to frequency domain, the temporal dependence goes away. And that means I want each of my frequency component to approach a delta function with support at RF. To achieve this, I define an objective function with this form. The integration here is over the entire model space, and I want to minimize this. This objective function was first introduced by Backus and Gilbert in 1968 in their paper where they studied the resolution properties of inverse problems. And they call it the delta-ness criterion. Now if I insert and substitute u from the weighted sum I just showed you and minimize this expression with respect to a sub i's, and after some algebra I end up with a system of linear equations which I can compactly show as shown here. Here, gamma on the left is an n by n matrix whose elements are computed with the integral shown below. The g's are the Green's functions, star is the complex conjugation, and if we have a good estimate of the velocity model of the medium, we could compute these Green's functions numerically. So we can compute gamma. G star on the right is an n by 1 vector whose elements of the complex conjugates of the Green's function associated with the source at each station and recorded at the target. Now, due to reciprocity, this Green's function is the same function that we would have recorded if the source was at the target and was recorded at the surface. And this makes the new method, what I'm trying to explain, very useful in applications like earthquake or microseismic event location, because this is the geometry that we would have in a surface microseismic survey. And finally, A is an n by 1 vector, and this is what we invert this system for. And remember that we are solving this equation in the frequency domain, so we have to form this system of equation for each frequency independently and solve it. And after we have done that, we can take all these AI of omega components, which we have computed, back to the time domain. And this gives us the optimal time signals that we require to get the objective, which is an impulsive function at the target. Now I have done this computation for this simple numeric experiment I showed you before. Remember, we had a 2D model with 5 stations on top. I will show you only the optimized trace for station number 2 as an example. And I will compare it to the trace that we would inject in the time reversal method. Here on the left, I'm showing you the time reverse signal, and on the right, the newly optimized signal which was computed with the new Backus and Gilbert method. As you can see, the signal on the right has higher frequency content. And finally, I would like to show you how the focusing result of the new method would compare with the focusing result I showed you earlier by the time reversal method. So this is the old result, time reversal, and now I show you the new result. So time reversal, Backus and Gilbert. So I hope you agree that we have managed to get better focus with the new method. And the fact that the size of the main lobe is more compact. And at this point, I have talked about the general things I wanted to explain to you about the new method. And from now on, I will talk about some interesting research opportunities and some interesting aspects about this Backus and Gilbert. The first thing I want to talk about is that even though we have managed to get a more compact focus, we'll still have energy at areas away from the target. And we would ideally want to have less of this energy. And the reason, and the way we can approach this is that we should step back and look at our objective function. This objective function that I use, basically we're asking it to give us a delta or impulsive source at the target. And it turns out that this is not the only objective function and probably not the best one. In fact, Backus and Gilbert themselves in their paper introduce other possible objective functions. One like this one, which is again a delta-ness criterion. However, here we minimize the first line W with respect to the subject to the constraint on the second line. And the interesting thing about this objective function is the appearance of the factor R minus RF squared. This factor, in effect, penalizes energy at locations R which are distant from RF, the target. So in such areas, R minus RF increases. So if you have energy there, W will be large. And by minimizing W, we effectively suppress the energy at locations that we don't want. The constraint on the second line is necessary because U equals 0 is a trivial solution for the minimization on the first line. And to avoid that trivial solution, I've included this constraint. Next, I want to talk about the connection of this new method with the time reversal. Although it might look that the two methods don't have much in common, as I'll show you, they are more related than it's obvious. So going back to the system of linear equations, gamma is in general a dense matrix. That means it has non-zero elements all over. However, if I consider a special case of gamma, where it only has diagonal elements and zero off diagonal, and the diagonal elements are equal, or more simply, if I just substitute gamma with identity matrix, then what I would get is this new system. Now remember that we are solving this new system of equations in the frequency domain. And in frequency domain, complex conjugation that you see on the right corresponds to time reversal in time domain. That means by choosing a special case of gamma, we have reduced the Backus and Gilbert method to the time reversal. And this is important because it shows us that the off-diagonal elements of gamma are important in determining the way we design the traces that we inject from each station. In other words, we want to trace for each station to be designed not only with respect to the complexities in the medium and target, but also with respect to other signals injected by other stations. And finally, I would like to talk very briefly about the possible applications of this method in imaging. Let's have a look at a single shot experiment. Here I have a shot at RS on the surface, a bunch of receivers at RI, and an imaging target at RF. Now, reverse time migration computes the value of the image at RF by forward propagating the source wave field, back propagating the receiver wave field, and applying an imaging condition, for example, a cross correlation. Schuster defines the reverse time migration process for each shot with this equation in the frequency domain, where here the G's are Green's functions, star is complex conjugation, and D is the data recorded on the surface. The summations are over the station numbers and frequencies. Now, Schuster singles out the product of the two Green's functions, highlighted as gold here, and calls this product the migration focusing kernel. I don't have time to go into much detail now, but I invite you to read my report if you're interested to know more. However, the point I want to make is that this focusing kernel can be optimized using the same or similar method that I showed you today. And if we do that, we are in effect managing to take out the detrimental effect of acquisition footprint or incomplete acquisition and other problems I told you, like attenuation, and effectively improve the resolution of the reverse time migration. So let me summarize the talk by reminding you that we cast focusing as an optimization problem in the hope that we can go beyond the limitations that reverse time or time reversal processes encounter. We introduced a new method we called Backus and Gilbert, and I showed you that this new method has promising applications and can provide interesting research ground in areas such as microseismic event location and also in imaging. And with that, I would like to thank you very much for listening and open up for questions.